Bismillahirrahmanirrahim. So we are discussing about the discrete time Fourier transform. So it refers to the chapter number 4 of the Krokis book. So please go through that book with some example problems as well as the problem in the exercise. Okay, so it is also available in the webs in the different sources. You can download the solution as well. So first of all, you can try it, and then you can try to solve the problems. And if you found any concept difficult to understand, then we can also discuss about that, because this is the time when we can think about the concept, and as well as to clarification those concepts for the future study. Okay. Okay, in the last class, I have also mentioned that today's class, I would just like to discuss about the realization, practical realization of the convolution sum, because in the time domain, we have done the convolution, but in the frequency domain, we have done multiplication. So how the convolution actually refers to the practical task or the practical scenario from the circuit point of view. Would like to discuss about that. Before going to that, I just, as I have always tried to discuss on the Euler's equation. So how do you understand this concept that we are talking about the cos omega t? Let's say omega t is equals to, we may have the phase delay or not. If we think that, okay, the phase delay is 0, in that case, we by using the Euler's formula, we are writing e to the power j omega t. It can be the t value or theta value. It depends on the concept. So we can here we can if we want to take t, then let's say we can start with the analog frequency omega t is equals to e to the power j omega t plus e to the power minus j omega t divided by 2. So the thing is, this is an equation. How do we represent in the graphical pattern so that we can understand this equation? So how could we represent this equation in the graphical way? So let's start with this. This is the real axis and this is the imaginary axis, as we all know about this. Let's say we are indicating e to the power j omega t. So at the beginning, when the t is equals to 0, and the value theta is equals to, of course, the phase is 0. Here, these two concepts, one is omega, which represents the angular rotation, and the t is the progressing with respect to the omega. So at t equals to 0, we are at this level. Let's see, we are at this point at t is equals to 0. So if that is so, then we can also write in other domain with the value where this is the amplitude of this function, amplitude of this function. So I just like a, and in this axis we have t. So t is progressing. So here t is equals to 0. As we are progressing, definitely we are progressing in this way. Okay, at t equals to 0, what we have found, we have got the amplitude. The real part of it is like this. And whenever it is moving, how that will move, whenever the t is progressing, of course it will be moving in this direction, the positive direction, because the theta, the phase is positive when t is increasing. So for any time period, whenever the value is here, let's say for a particular moment, this is t1, at that moment we got the amplitude here, the amplitude function is here. Similarly, whenever it is moving to this point, we can represent this t value with the theta as well, or also with the t value. So as you can understand, so at this moment it gives the magnitude is equals to 0. As you can understand, this is a continuous time section, so it will looks like this. Similarly, when it goes here, of course, in that case we got the magnitude looks like this. When it comes to this real portion, it gives the negative maximum value like here. And when it is proceeding again to this point, let's say it will proceeding with the time scale as well and getting some value like here. When it's put it on the imaginary axis again, it gives it the 0 value. So similarly, when it will proceeding and goes up to this, you will have some values. At this moment you are getting some value here, and at this moment you are getting some value there. And now if I add those points together, we can find this kind of scenario. And if we think about this, this is nothing but a cause signal. So this is a cause signal where we got the amplitude as well. What is the amplitude here? Of course, the amplitude here is 1. So the maximum value we got 1, and this is -1, and this is again 1. So according to the equation, we have concentrated on this first portion. Now we need to add another portion, and for that, let me draw the same thing again here. Now this section is e to the power minus j omega t. This minus reflects that it will rotate in the clockwise direction. That means the opposite to the e to the power j omega t in the Cartesian plane. So again, if we draw the same thing like previous, let me just do it side by side. This is the time, and this is the magnitude found. From the diagram, we can easily understood that again, where it will start at this point, and that's why the magnitude is here. And now it is rotating clockwise. So when it will be there, we got the magnitude here. When it comes to the imaginary axis, it definitely falls to the 0 value. And again, with the same logic, it will proceed with the time, and it will just proceeding like this. If you follow the whole process like the previous, you will find that you are getting those points as I have mentioned earlier. So at this moment, you are getting again this point, and when it will be reaching to the origin again, the starting point, you'll got the same point. So now again, whenever you are adding those points, you are getting this kind of signal. What is the amplitude here? Again, the amplitude is 1, because we are talking about e to the power minus j omega t. What is the magnitude? Magnitude was 1. The highest value is 1, the lowest value is -1, and you have this is 1 as well. Now, according to the Euler's formula, you need to add those together and then divide by 2. Definitely, what we can do, if we add those together, what would be the amplitude, starting amplitude? It will looks like 2, the maximum value 2 and the minimum value is 2. So the peak to peak value is 2 minus 2. So you'll have you can understand that if we add those together and divide it by 2 each and every point, it actually gives you the cos omega t. Here, how fast this processing will be done. For example, I can take another color. How fast the processing. Can you see my screen? Are you there?
Yes, sir. We can.
Can you see my screen? I'm not sure because the sharing option probably makes some problem. Okay, so the outline was not shown. Okay, so if you we are talking about the frequency. Whenever the omega is higher, it shows that you have the higher frequency. The speed of the rotation, actually depends on the value of omega. So then you have the higher frequency component like this for higher frequency, but the processes remain the same. So this is how we can prove that, okay, the Euler's equation definitely with the graphical representation. Similarly, if we think about the sine signal, so we can represent sine omega t is equals to e to the power j omega t minus e to the power minus j omega t divided by twice j. Okay, so so how we can show it? Definitely with the same principle, we can show that. However, if we think about the Cartesian plane or vector plane, we can also understand the pattern very easily. Let's say for a particular theta value, that means for a particular proceeding of the signal after specific amount of t, let's say the e to the power j omega t, definitely it will proceed, and you will find this signal like here. Okay, you will find the signal. So this is what, this is for a particular value of the theta. So you can write in this way, this is e to the power j omega t, and where t is not equals to 0, this is a proceeding. Or sometimes we can write in a way that it will have the theta value. Okay, so anyway, we know that it is proceeding to the anti-clockwise, since we have positive here. For that particular moment, if we consider e to the power minus j omega t, well, it will be definitely using different color. Let's take red. It will be proceeding here, and it is e to the power minus j omega t for a particular value at the same value of the t. That's a, we can just make a t1, and this is t1. That will make sense. And now, since we have a negative value, so if we want to add those together, so a negative value means in the vector diagram that can be extended in the opposite direction. So this is basically a minus e to the power minus j omega t. Now, if we want to add those two components, then definitely with the vector calculation, we'll find this result, and this vector is equivalent to the green vector what we have found previously. So this one, and this is the red one from this. Okay, so you know how to add those two vectors. And the resultant vectors, we got the resultant vectors here. Just different colors. Okay, so this is the resultant vector. So what is the amplitude of that? We'll find that this amplitude is twice of, you can find that what would be the value if we can have the value. What is the value? You can find this is sine omega t. This is sine omega t, where t is t1. And again, we have the same value there. This is again sine omega t, where t is equals to t1. So we got twice sine omega t1. And since that is in the imaginary axis, or I should say on the imaginary axis, there should be multiplied with the value j. And this is equals to what? We have e to the power j omega t minus e to the power minus j omega t. So from there we can write sine omega t for, these are the t1. So t1 is equals to e to the power j omega t1 minus e to the power minus j omega t1 divided by twice j. So you can take, this is definitely an instantaneous value. For instantaneous changes of the sine theta, you can validate the equation, Euler's equation as well. Most interestingly, why I'm representing this, because in many cases, when we are shifting from the sine, the concept of the instantaneous signal represented by sinusoidal signal to the exponential one, then we are facing some problem to realize practically. So what happens, because they are actually equal, but they are presenting in different manner. That is the difference. So that is why I'm just presenting it here to build up your confidence that those are very simple. Whenever you got this kind of function, you can move to this, because it will give you some kind of advantage to do the integration and the differentiation. For mathematical calculation, you know that you need to perform integration and the differentiation for many various purposes. So it is always better to go to use the Euler's formula and jump to that. And whenever you need, you can come back to your original signal representation as well. Okay. I was talking about a system, a representation with convolution. We know about the difference between convolution and the correlation, and this is very simple. In case of convolution, of course, we need add a extra portion that is called folding operation, and afterwards we make the shifting. And for each and every point, for the discrete signal, since we are talking about the discrete signals, for each and every point we are making the multiplication, and then we are summed it up for each and every case. But how can we realize this with the practical circuit? That is the motivation of this section of the lecture. Let's start with the definition. Let's say we have one signal xn, and we are putting it or giving it to the system, and the system is represented as the impulse response hn, and we got the output yn. So how many samples you have in the xn doesn't matter. It can be finite, it can be infinite. Similarly, in case of hn, it can be finite or it can be infinite. If that is a finite, then it is a finite impulse response. Or if that is infinite, then infinite impulse response. From this concept of a system, we can write yn is equals to, let's take all the samples of the input k is equals to from minus infinity to plus infinity. And of course, this is equivalent to xn. Why? Because n is a dummy constant. So we can replace it with another constant k, where it shows that, okay, we have all the samples. We need all the samples, and multiplied with h, we can write it in this way: folded version for the zeroth sample. Zeroth sample means n equals to 0. For other samples, it is a function of n. It is a function of n. So I believe that after today's lecture, you do not need to memorize this equation. You can understand from the graphical representation. I believe you already understood that. Still, I want to express it. Okay, so it is also equivalent to. So what does it mean practically? This part. This part shows that you have your xn, whatever the xn. Okay, let's say this is the xn, and you can think of, okay, we have different data points practically, and we already have the hn. So first of all, what we are doing, we are taking xn, the full bunch of xn, which is actually represented by this summation of k is from minus infinity to plus infinity xk. That actually belongs to hn, because all the samples. What is k? Any value from minus infinity to plus infinity. So it actually refers to the full stem of the xn, your input. So this is our input. In the time domain, let's say you are having, these are the present value. So I'm putting, this is a 0, this is for 1, this is 2, this is 3, 4, 5, and so on. So this is your xn, looks like. So those are the future values, and 0 is the present value. Now you have hn. Let's make it a little bit smaller to understand the process. So you have 3 samples, and make it again very simple. Let's say this is hn. This is hn, where this is n equals to 0, 1, and 2. So you have some sample value. Now what we are doing practically, we want to here this equation represent that. First of all, you need to fold this. Why? To find the value of yn. Now we are looking for the yn spectrum, which is completely unknown to us. So we do not know anything. So let's think that this is n0, and we want to find y0. So if you want to find that, so of course we need to put 0 here, and this is h minus k, where k is from minus infinity to plus infinity. That means that you need to fold your hn. Whenever you are folding that means h minus k. Now and then I'm taking hn and k. Don't confuse with that. The k and n, they are equal. N represent all the samples, and k is now also represent all the samples, because k is from minus infinity to plus infinity. So when it is flipping over, so then how does it looks like? It looks like this. This is your h minus k. So this is a 0th sample, n equals to 0, and they just flip it over. So they are a -1 and -2. They are just flipping like that. And now they are interacting each other. So only this sample x0 and h0 basically interact, and there is no other interaction. So you do not need any summation, and whatever the value you got there, and you are getting that result. Now in the second case, whenever we are talking about n equals to 1 for y1, what will happen? This value will be 1, so it will be shifted which direction? If we are having a negative, that will shift it right. Since this is a folded and positive, that will also shift it right. So it will shift it right. And then what will be the scenario? The scenario will be like this. We have the folding version. I'm just writing this. So we have the interaction between 1 and 0th sample of this, and 0 sample of xn with the first sample of hn, and this sample will not interact with anyone. And since we have two samples interaction, 1 and 2 interaction, afterwards you need the summation, and the value will be presented at this point. That is the whole things we have done with this equation. However, if we change that with this equation, let me write that this is yn. I should take another color. Yn is equals to hk, where k is again from minus infinity to plus infinity to grab the whole impulse, and x n minus k. What does it mean? Now your hn will remain stand still, and your inputs will just flip it over. That means we have the folding operation of the hn, the xn, which actually means in this way practically how that equation relates with our practical scenario. I should write the equation here again. Yn is equals to hk. K is equals to from minus and plus infinity. What means it means that you are taking all bunch of your impulse response. That means let's take an example here. This is an impulse response. Make it simple. Okay, this is the impulse response, where let's say this is 1, this is 2, and this is 3. Those are the amplitude, and this is 0, 1, and 2. This is what your hn. Okay, if you just mention me, if you just tell me that, okay, if I make it like hk, is that fine? In a sense, it is not good enough, because by the value of the k, what we are presenting, that is a constant, and by hn it represents that is a sequences of signal. That is a sequences of signal. So hn is equals to basically k is from minus infinity to plus infinity hk, or you can say for this practical example k is from 0 to 2 for this example. That is, they are equal hn for this case. Okay, fine. Now this is our hn. Where is our hn? In the block diagram, this is our hn. Physically, you can find whenever you are, let's say you are a human being, you are the input. When you are inside your system, which value you will experience first, which value or which amplitude you are experiencing first. Definitely you are experiencing 3 first, then 2, and then 1. And since this is a discrete domain, definitely you are getting one by another. Okay. Okay. Now let's say how looks like x n minus k. For example, the x is looks like this. Okay, this is the value. I'll just think that this is the present value, and we have some past values. Sorry, future value. We can have some future value. So this is at 0, 1, 2, 3, and whatever the values are there, you can write it there. So again, practically, which value will interact with hn first? Which value? So let me give the amplitude of this. Let's say this is 2, this is 3, this is 1, and this is 0.5. which value should interact with H0 first? Can you answer? Practically, which value should interact with H0 first? I'm asking which value of Hn should interact with the Hn. Which value first interact with Hn practically in the practical scenario? Yes, 0, 2. I can't hear it. Yeah, 0, 2. You are now probably audible.
Sir, H0.
H0 and X0, they will interact first.
Yes, sir.
And so it will be definitely logical that we can make a sequence of X in such a way. Who will make the interaction first? This one. So that is the value 2. Whenever they will make the interaction with H0, there is no other interaction. Whenever it proceed, this sample proceed to make the interaction with 2, then which sample is interacting with H0? Definitely X1 will interact with H0. That means sequentially, we can say that first this will interact, then second this will interact, the third this will interact, and this fourth will interact. So if we talk about the samples, because in the digital circuit we are making the clock pulses, for each and every clock pulses, for the first clock pulse, now who will interact with whom? This will interact with this. This is the first clock pulse. In the second clock pulse, if I take another color, I'm running short of colors. Okay, let me take green. In the second clock pulse, this will interact with this, the second one, and this second one will interact with the first one. So that's why this is logical that the Xn can be folded. So it makes the understanding more clear. So first of all, that will be folded. So this is the 0th sample. So one sample will take into the -1 sample, and 2 will be taken to the -2, and the third one will be at -3. So that's why we need the folding operation, that is x minus k, where k is from -infinity to +infinity. Now they are dragging one by one, and they are interacting with each other, and they are making the output. Okay, I can present a practical example here, just to make the idea more simple and clear. Let's take an example. In the Procreus book, you will find this. The impulse response is given as 1, 2, 1, -1, and Xn is equals to 1, 2, 3, and 1, where this is the 0th sample and this is the 0th sample. Okay. Now practically you can find it with your equation, whether xk hn minus k, you know that k is from -infinity to +infinity, or with hk xn minus k, with that equation, helping equation, that is fine. But graphically, you need to understand this. That will definitely help us how we can understand this graphically. As you know that this convolution, is only possible for LTI system, linear time invariant system. Otherwise, it is not possible. What does it mean actually? Let's say for x0, what is the value of x0? That is equals to 1. If your input is 1, so first who will interact with Hn? Definitely this one will interact. With whom? With the impulse. First, this will interact with this, then it will interact with this, and this. Basically, what we can say very simply, if you do not have any sample here, you do not have any sample. If you only have Xn, what is the output? Xn equals to 1. What would be the output? That should be like this, because that is the impulse response, isn't it? You agree with me?
Yes, sir.
Yes. So we can write it in this way. Let's say this is n. So if x0 is equals to 1, so what would be the output we will get? We'll get the output as the impulse response. So we can write here, take red color. So it will be 2. So I'll put 2, then it is 1, and there is a -1, and this is +1. That is the output. So this is exactly like Hn. Now what we can do, we can draw for xn is equals to, x1 is equals to what? X1 is equals to 2. This was 2, then 3, then 1. Now the question is, whenever you are at this moment, you are actually shifting. You are shifting. So since there is a, what kind of system is that? LTI, linear time invariant. So if that is shifted, the input is shifted, of course the impulse response will be shifted accordingly. So that means it actually takes some delay. What is the sample delay? 1 sample delay. After 1 sample delay, these two will interact with the sample, and you will get basically this kind of output. What would be the output? It will actually multiply with Hn. So of course the output should be like 2 into Hn, but since there is a time delay, it will be like 2h into n minus 1, because there will be some delay, and the delay is a single sample delay. So we can write it like it. N, this was the 0th sample. So everything will be multiplied with 2. So that's why I need some more space. N, it will multiply with 2. So previously it was 1. So there will be shifting and multiplication of 2. So I can write straightforward. It will be 2 here. Then it will be, the second sample will be 4. Then this will be 2, and there will be -2. So 2 minus 2, this is 4, and this is 2. So this is basically twice Hn minus 1. Okay. Similarly, we can now understand when 3 will interact with the impulse response. Since this is a LTI system, it will be shifted 2 samples, because this is 0, 1, 2, 2 samples, and multiplied with 3 value. So if I draw it here, we can write for x2, where the value is 3, the response looks like this. This is the 0th sample position. Since that is shifted 3 sample, the first sample is 3 now. The second sample is 6. Third sample is again 3. And the fourth sample, so this is 0, 1, 2, 3, and the fourth sample is -3. 3, -3. You have another samples to finish it out. This is again for x3. Here 3 means 3 samples delay is equals to 1. So definitely you can find that again, that will be nothing but a impulse response, basic impulse response, but that is shifted by 3 samples. So we have 0. This is first sample 1, 2, 3, 4, 5. Let's say do it like this. So from second sample we have 1 again. This is 2. This is 1, and this is -1. Okay, so if I make it a little bit smaller, the window, you may find it very interesting, the concept. If you can think of the whole scenario, practically what happens? Practically, when this one interact with your impulse response, basically it actually make the interaction with one of your impulse. The location was n is equals to -1, and that's why it makes a value 1 at the location of -1. So this is that value. So let me choose black color here. This value. Now, when it proceeds in the second clock pulse, this one will basically interact with 2, and that will make the value 2 here. Whereas this 2, that means this is the second one, it actually interact with 1 at that moment. And that's why they are making this value 2. The amplitude 2, so this is Hn 1, 2, 1, -1, and Xn is equals to 1, 2, 3, and 1. So at the very beginning, whenever we are talking about this one, just because this is the starting sample, let's say we are talking about the temperature. This temperature is hitting the device, that means your impulse response, Hn. This is your device. Your device is basically characterized by the impulse response. It is already been defined. So this one is first interact with this, and it actually produces at that very moment, it only produces this one, nothing else. Nothing else. You do not get anything. So we can say that what is the value at that location? What is the value? The value of y -1 is equals to 1. Definitely 1. There is no other value. Now, if we proceed, that means whenever in the second clock pulse, definitely this 1 will interact with this because it is folded, and this 2 will interact with 1. So there are 2 samples you got, 2 interaction are there. So 1 is already proceeding in the second clock pulse, so they will interact with this, and 2 is the first time it is actually entering to the system, so it will interact with 1, and it can be realizable with this graphical representation. So this is the 2 value. So 1 is interact with 2, and 2 is interact with 1 at the first time, and the value is 2 here because it is the first time it interact. So what you need, so within that time period, it will be shifted. It will be shifted. So what is the value at y0? At y0, we are getting only these 2 interaction. So this is 2 plus 2. That is, of course, this is 4. Now at 3 clock pulse, of course, at 3 clock pulse, at that moment, this will definitely interact this. 2 will interact with 2 and 3 will interact with 1. Definitely 3 is the first, this is the first time it actually experiencing 1. In the circuit, what are those elements? They are amplifier. They are just the amplifier circuit. So they amplified your input signal with those values linearly because we have LTI system. So you can understand that the HN is not changing. They are actually some sort of an analog circuit. We can represent it like this, that we have an amplifier. What is the amplifier's symbol? This is an amplifier. This is another amplifier. Another amplifier, like I can put 4 amplifier, where the 4 amplifier, one is 1, another is 2, another is 1, and there is a -1. There are 4 amplifiers. So these are just having some adder circuit. They're putting to the adder circuit, and this actually gives your output, sample by sample output. You are getting your sample by sample. Now at the very beginning, because we are just folding the operation, this one interact with this sample, because that is the chronology, how you can find, and there is no other interaction. At the second level of the second clock pulse, this 1 is shifted there and the 2 will enter here. At the third clock pulse, this 1 will be there, this is 2, and this is 3. And what will be the value? Of course, you can understand 3, 4, and 1. So that is 8. Of course, you can find this is equals to 8. And of course, from this graphical representation, we can also find where is Y1. This is 1, this is 4, this is 3, and this is 0. So that is also 8. In the fourth clock pulse, in the fourth clock pulse, what will happen? This will be 1, this will be 2, this will be 3, and this will be 1 again. This is the fourth clock pulse. So they are shifting, definitely. This is a shift operation. And what would be the value? We can find 1, 6, 2, and 1. So if you add all those together, you can again find 8. And if you look at this diagram as well, okay, so there is a -1 as well. Okay, so you can also find what is the value of Y2. This is -1, 2, this is 6, and this is 1. So of course that is altogether 8. Similarly, if you put another clock pulse, what will happen? The 1 will be shifted here, 3 will be shifted here, 2 will be shifted here, and 1 is out of the range. Okay, they actually passes through the circuit. So 1 passes through the circuit, so it doesn't have any impact to the circuit. So then what will be the value? 2, 3, and a -2. So that will makes 3. Y3 is equals to 3. Similarly, it will have 1 and 3, and you'll find whatever the consequences. So that is how you can think of your impulse responses and the circuits. Okay, so practically we can think of the circuit in that way. Just a minute. So we have our HN, and how do we can represent that? We are representing by the block diagram. It actually be a circuit where you can represent. Okay, we have some amplifier and adder circuit combinedly make it sense. Okay, so that is the representation we can understand with the graphical values. So it is always fine, very interesting to understand the convolution, because in many cases we are using this convolution to understand the process itself. Even in the filter and the filter design, we are basically doing the convolution always, and we are searching the output based on the impulse responses. When we'll talk about the filter design, mostly we try to design our impulse responses, so how they will actually interact between themselves. For example, if we have the impulse response is a delta function, can you prove that what would be the output frequency if I am giving a frequency like a 30 hertz signal to this impulse? What would be the output frequency? And can you realize that, or can you make it sense with the graphical representation? Of course, you should. For example, if I take this example, very simple, but I believe this is effective in a way. So let's say this is a sinusoidal signal. Since we are talking about the discrete signals, so then we can discretize it, make it simple as possible. Okay, so we have several samples, and let's think that, okay, we have several samples. Now this is of course at n equals to 0, and this is equals to 1, this is 2, 3, 4, 5, and so on, and this is our xn. And now this is a single frequency value where you can definitely, whenever it is a discrete signal, this is, we have omega, and omega is equals to twice pi small f, where twice pi small f is equals to f divided by fs. I'm talking about this small f, the capital F is 30 hertz. That's what I start with, and whatever the sampling frequency, depending on that, you got the value of omega. So let's say for a particular sampling frequency, whatever the value, let's say this is 60 to make it simple. So this is pi. So omega equals to, let's say, pi. For omega equals to pi, there is a signal, and it given to the impulse response Hn, where Hn is equals to a delta function. If that is so, then what would be the output and how we can understand those? If I use the eraser, okay. So the signal looks like this, of course. So stem 0, stem like this, and okay, conventionally like that. So which sample will first interact with this? So you know that your impulse response like this, at n equals to 0, the value is 1. So from our past experience, we can understand very easily that at the very beginning, this sample will interact with your impulse. And this is at the location of 0. And what would be the value? 1 multiplied with any value that will actually belongs to that value. Now, after interacting with the impulse, definitely this will go out of the circuit because they don't have any other things to interact with. So it is out of the circuit. By this time, in the second clock, who will interact with the impulse? So in the first clock, we have the interaction like this one. In the second clock, this one will interact with this, and of course, it actually remains to the same nature because it multiplies with 1. And if we repeat the things, definitely, and afterwards, this will go out of the circuit. Then 0 multiplied with 1, you have 0. Then minus some value multiplied with 1, you have that one. And the shifting is also operating because this is a LTI system. and so on and so forth. And at the end of the day, what you are finding? You are finding exactly the same thing in the output. This is in the time domain. We are doing the convolution in the time domain, and we found that, okay, we are getting exactly the same signal out of them. And now if you have any sort of signal, any arbitrary signal, okay, of course it is a discrete signal. Let's say this is a discrete signal. Whatever the discrete signal, if the impulse response, if that is the impulse response, you got the same output, it means that this kind of filter actually preserves the frequency. It preserves all the frequency. Now if we move to the frequency domain representation, what is the frequency domain representation? Magnitude response of the delta function. We have already know that this is from pi to minus pi to plus pi. The magnitude response is 1 from minus pi to plus pi. What does it mean? You have, I have drawn it, you have all the frequency component. You have all the frequency component inside the delta function. And if you are put a input frequency, let's say 30 hertz somewhere else, since these are the relative frequency, it is not exactly 30 hertz. This is basically f divided by fs multiplied with twice pi in the omega format. Then what will happen? They will multiply with each other, and this is a proof. That means in the time domain, I have already proven that, okay, it will preserve the same signal. And why it actually preserves the same signal from the graphical representation in the frequency domain, we can find that, okay, this value, what is the amplitude, what is the frequency, that only multiplied with this value, because always you have 1 there, it will multiply with that, and exactly you will get this value at the output. So if you multiplied with that, if this is yn, the frequency domain of yn, we should write y omega, you will have the same thing out of this. This is pi, let's say this is minus pi, and this is f di fs into twice pi. And the frequency domain representation also give you the same sense in the output. So that actually preserve your original signal. How do we understand the impulse response of a system? So very practical point of view, you have a system X, you do not know anything about this. Whenever you are giving a delta function as an input, whatever the output is known as the impulse function. This is fantastic. So this phenomena basically it gives you the characteristics of this system. Afterwards, if you take it as a system response, then you can put any arbitrary input and you get the relative output, and this is very logical. Why the impulse response is very important? Because impulse response is the characteristics of your system. Why? Because as we already know that this impulse actually have all the frequency component, and this is nothing but, any system is nothing but a filter. So if you want to check your filter, let's say if you want to check your filter, you have a filter, physical filter. So you have a physical filter. If you want to check it, whether it is a good filter or bad filter with different, let's say, sand pieces. So you have some bigger sand pieces, you have some small sand pieces, you have very tiny sand pieces like this. Now, for what kind of sand this is good enough for the filtering? So which one you actually pass and which one you block? So you understand whenever you are giving all kind of sand pieces. And here the delta function is the combination of all kind of frequencies. And that's why this is very logical that first of all, you will check your filter. You will check your filter with the impulse response. In the frequency domain, how we can understand this concept, as I already mentioned, that the frequency domain response of a delta function, this is your input, let's say, this is your input, minus pi to plus pi, and this is your system. You are just searching about the system. What is that? How it looks like. Let's say you make a multiplications. Multiplication means you are making convolution in the time domain, and you found that the output is like this. The output is like this. This is your output. This is y. I should write y omega, and I should like not delta omega. Delta omega. These are the in the frequency domain. So in the frequency domain, this one will multiply with someone, and afterwards you are getting this. Since this is a 1, all are 1, so what would be the value there? You can find that exactly you have the same as the output. Otherwise, there is no other possible way. They will be the replica. And now we can say that, okay, this is equals to the same of h omega. And that is how we can say that, okay, this is our filter response. And from there we can find, okay, yes, of course, this is a low pass filter or high pass or band pass filter. Now you can change the characteristics of this. So this is in the frequency domain. From that, you do the inverse Fourier transform, and you can find what is the value of Hn. And whenever we are definitely, you have the experience to design the practical filter, both FIR and IAR. So we need to just changes the value of Hn. Okay. So I believe that is enough for today. So if you have any question or comments, you are free to do that. If it is possible for me, I will discuss on those comments or your question. Any question or comments? From the next class, we'll start the Z transform and how to design the filter with the Z transform. That will cover 1 or 2 classes, and after that we'll move to the the filter design. Quickly make some review on that, and multi-rate signal processing, and also wavelet transform in the subsequent classes, inshallah, after the Eid vacation. Okay, if you don't have any comments or question, then we can stop the recording for today. Thank you.